Hello everyone, welcome to my presentation. I'm going to present the paper titled as Port Capacity Leasing Games at Internet Exchange Points. I'm one of the authors of this paper. My name is MD Ibrahim Ibne. This paper got accepted in GameNets 2021, and so let's have a look at the content of the presentation. So at first I'm going to talk about the introduction, where I'll talk about the background and the motivation. Then I'll compare our works with prior works. Then I'll continue my presentation with system model and properties it has, followed by price of anarchy analysis, which then will be bolstered with the simulation results, and then I'll conclude my presentation. The internet service providers, or the ISPs, they usually form a connection known also as public peering at an IXP to exchange traffic between them. Now, the peering between ISPs, it has been increasing over the last few years, and in the last 10 years, it has increased 3 times, so which resulted in flattening of the internet, where all these ISPs are connected to one another, exchanging traffic. Now, exchanging traffic at an IXP, it usually improves traffic quality of services. It means that it will it will have good effect on the delay. The delay will be less, and the ISPs will have the option to exchange traffic directly without the help, without needing any help from any third party. Now, this port capacity leasing decision of any ISP is actually dependent on each other. So when one ISP is trying to decide if it's going to lease some port capacity, its decision is going to be dependent on all the other ISP's decision. So what we have done here is we are trying to analyze the port capacity leasing problem from a perspective of non-cooperative game, where all of these ISPs unilaterally tries to minimize its cost, and so they are taking this decision unilaterally, not as a pairwise. To compare our current work with prior works, what we have seen is that there are a lot of work which try to investigate the effect of IXP pricing on peering relationship. Now, most of those work, they focused on pairwise equilibrium from the perspective of the ISPs and from the perspective of network formation games. However, here in our work, we are focusing on Nash equilibria. We have assumed that the ISPs are going to peer at the IXP, but the main focus is going to be the port capacity leasing problem, where how much port capacity an ISP should lease are going to be decided. Previous work focused on, whereas the previous work focused on finding the amount of traffic that is needed to be sent through the IXP and how much traffic is going to be sent outside of the IXP or through some transit provider. Now let's have a look at the system model. So this figure portrays the system model, where as we can see, if let's say there are two ISPs present in the IXP, there could be of course more than two ISPs, but for this specific system model for depiction, we have used only two ISPs here. So let's say ISP I has a port I, and the port capacity is denoted by Xi, and also ISP J, it has a port capacity of Xj, and also there is a shared switch fabric which the IXP has to process the traffic. Now then, if the ISPs, let's say these ISP pair IJ, it wants to exchange traffic, then those traffic, the Yij, which is the traffic flowing from I to J, and Yji, which is the traffic flowing from J to I, is going to face three kind of delays mainly. One is in the port capacity of I, in the port of I, the other one is in the shared switch fabric, and the last one is going to be on the other port. So the cost of ISP I, it can be written in this form, where this CP terms is actually depicting the cost function or the delay function that is being faced at the ports, and we have summed it over all j, since there can be more than more than two ISPs present in the IXP. So all the other ISP j values will have some congestion in the cost of the ISP I. Then we have added another term CLXI, which is actually portraying the lease capacity, the port capacity leasing cost, and then we have the switching delay or the shared switch fabric delay here. Also, if we assume or if we denote Yij, the summation of Yij over all j, to be the amount of traffic that is being actually sent outside from ISPi, to be denoted as Y underscore I, and all the Yji traffic summed over j, that means all the traffic that is flowing inside ISPi using a notation Y superscript I, then we can show that the cost of ISPi um, can be written in this form of equation. With the system model, as we have described in the previous slide, we have made some valid assumption. So the first assumption is that the cost of ISP I, it always has a unique minimum in xi if we know that the other ISPs, they are fixed with their port capacity, which is denoted by this x underscore minus I. Now, with this assumption, if we use Brouwer's fixed point theorem, we can show that an equilibrium for the port capacity leasing game, it always exists. Now, if we want to find out the total cost that the ISPs are facing as a whole in this game, then we just need to sum up all the ISPi's cost over the overall ISP, and then we get this kind of equation. So the port capacity leasing game, as we have modeled in the way we have modeled it, it can have multiple equilibria. One such multiple equilibria occasion can be demonstrated using this example, where we have assumed that there is only two ISP peering at an IXP, and Yij is equals to Yji is equals to 1, and we have a CP equals to constant. That means the port delay is not changing with the port capacity. Since this is a very simple example, that's why we assume that. And CS is a shared switching capacity, which has a function like this, and the port leasing capacity CL is equals to logarithmic of xi. Then we can show that every condition that satisfies that xi plus xj has a value of 12 is an equilibrium. Now, the theoretical analysis is divided in two parts. So in the first part, we have tried to analyze what happens when the switch capacity is fixed. That means the IXP is not changing its switch capacity according to the port leasing capacity. Now we can show that when this CSXI xy is only dependent on the traffic vector y and is not dependent on the strategy vector or the port capacity that the ISPs are leasing x, then we have a potential function which is given by this equation, and with that potential function we can show that this game is a potential game. So theorem 1 says that with our assumption 1, if CS is independent of X, that means it has a fixed switch capacity, then each ISP has a dominant strategy and the port capacity leasing game has a unique equilibrium. Since it has a unique equilibrium, so we can show that with the potential game analysis, price of anarchy is actually equal to price of stability, and which is bounded by a value of 2. Now, if we look at our game from a generalized perspective where the switch capacity can vary, then we have an example which gives us a very bad price of anarchy or POA. So for this example, let's assume that CP is equals to 0. So the port delay is negligible or close to 0. The switching delay cost is CS, which is given by this equation, and CL, the port capacity leasing cost, is 2 plus epsilon times the port capacity being leased. Now here the N is the total number of ISPs, Xi is the port capacity of those ISPs, and epsilon is just a small positive value. Also, we have assumed that Y underscore I and Y superscript I is equals to 1. Now, if it happens that all of the other ISPs without the ISP I, they have leased a port capacity xj equals to 1, then the cost of ISP I becomes equals to this equation. Now, as you can see, then ISP I will be motivated to keep its port capacity xi to a minimum, and which is actually equal to y underscore I, which has a value of 1. Now the total cost at that equilibrium, where all these ISPs are choosing a port capacity of 1, is given by this equation. Now if we look at the optimum solution, then we can see that we can find an optimum solution where all the port capacity xi, all the ISPs actually should have chosen a value of 2 if they wanted to minimize the whole cost of the total gain. Now the total cost at opt, or the optimum solution for this type of for this specific example is given by this equation, where uh, which gives us the price of anarchy, which is actually the ratio of um, cost at equilibrium divided by the cost at optimum, becomes very large and has a value of n over 2 for large values of n. So if there were like 20 ISPs peering at that IXP, then we can have a price of anarchy which is close to 10, which is really bad. Now if we look at the theoretical analysis for variable switch capacity, we can show that we can try to bound our port capacity leasing gain using the smoothness property. So from the smoothness property, we know that if any gain it holds this equation, where this x star is the optimal solution or the port capacity leasing vector which gives us the optimum value, and x is any other port capacity leasing vector, then we can have a price of anarchy which is bounded by this equation, where lambda and the value of mu is up to us to decide. Now we can show that if lambda has a value of 1 and mu has a value of half, then the price of anarchy for the current game can be bounded. Now theorem 2 says that if the port capacity leasing game has a it follows this condition, then it has a price of anarchy which is less than or equal to 2. So what is actually being portrayed by this equation? So it says that when the delay that is being faced at the ports is actually greater than the delay that is being faced at the shared switch, then we always have a price of anarchy which is less than or equal to 2. That means if the IXP, the shared switch capacity, is not the bottleneck, the delay is mainly happening in the ports, then no matter what kind of decision the ISP is made, always the price of anarchy is going to be less than or equal to 2. And as a specific and as a special corollary, we have shown that if both the delay function of CP and CS, they represents a MM1 kind of delay function or a queuing delay function, then the price of anarchy for this game, the game that we have analyzed, is actually bounded by a value of 2. With all those theoretical results, now let's have a look at the simulation results. So at first what we did was we collected a lot of data on IXP and ISPs from CADA and PRNDB. Now all those databases, they have a lot of information of the router, the port capacity leasing, and these sort of things for the IXP and ISP's perspective. Now using all those data, we tried to find out how the traffic matrix or the amount of traffic that the ISPs might have for one another to exchange. So then using that traffic matrix, what we did was we tried to implement a real life simulation scenario where the ISPs are going to exchange traffic with one another, and we checked the effect of shared switch delay. We tried to change the shared switch delay, the port leasing cost, and try to find out what kind of effect it has on the price of stability. Now as we can see here in this figure, we have used three kind of functions to portray the shared switch delay. Now here we have used linear, exponential, and queuing delay type of function. As we can see, we have used a factor beta which we tried to which we used as a proportionality constant for the shared switch delay. If we increase the value of beta, we see that the price of stability, it increases. Also, it can be seen here that the linear function, it increases very rapidly with the increase of the proportionally constant beta. So it gives us some idea that if we use a linear function for the shared switch delay, then it might give us a bad POS. Also, another thing is, as we can see, when the proportionality constant beta is really small, that means when the shared switch delay is really small, then the price of stability is also quite small, which is actually in accordance to our theorem. Then as you can see, if we look at the port leasing cost, then with the increase of port leasing cost, the per unit port leasing cost, which is actually the slope of CL, we see that the price of stability of the social cost, it actually decreases. However, we need to check what happens to the social cost. As we can see, with the increase of the per unit leasing cost, the social cost, it actually increases. That means the ISPs are facing more cost to send the traffic through the IXP. So although the price of stability is decreasing, the increase of social cost is going to drive away the ISPs to look for a cheaper option. To continue our results for the simulation, here are two more results which focuses on the how does the price of stability changes with the traffic symmetry, and what is the effect of number of ISPs peering at an IXP. Now, as we can see here in this figure, we have changed the coefficient of symmetry alpha, where alpha equals to 1 means all the traffic are similar, that means a symmetric traffic, and if it's 0.2, it means that the amount of traffic, the minimum amount of traffic to the maximum amount of traffic has a value of 0.2. So it's actually a ratio of the minimum amount of traffic to the maximum amount of traffic, which gives us the coefficient of symmetry alpha. Now, for three different kind of congestion function for the switch, we have plotted this, and as we can see, with the increase of coefficient of symmetry alpha, we get increase in price of stability. That means no matter what kind of function we use for the switching delay, as long as the traffic is more symmetric, the price of stability seems to be increasing. On the other hand, here in this figure, we have plotted the price of stability of social cost with the increase of number of ISP. Now, when there are only two ISPs peering at an IXP, the price of stability, it starts at quite close to 1.15, and then with the increase of number of ISPs, it increases. And as we can see, it actually is quite closely resembling a logarithmic curve. Hence, to conclude our presentation, we see that the port capacity leasing by an ISP, this kind of game, we have modeled it as a non-cooperative game. So after modeling this as a non-cooperative game, we have shown that if the switching capacity, if it's fixed for some IXP, so that the delay is not changing for the switches, then we have a potential gain and we get a price of stability less than or equal to 2. Then under some reasonable practical assumptions, we have shown that the general gain, the whole generalized version of the game, the price of anarchy, can be bounded by a value of 2. Now also we have shown that through our simulation that our theoretical claims, those things are actually true, and we have shown that for practical traffic models generated using real life IXP data, the price of stability is quite close to 1. So that was all from me. If you have any question, I am happy to answer it. Also, if it's going to take a lot of time, if it's an elaborative question, then you can email me and I will be happy to answer you.